Um, okay, let's talk a little bit about the different types of solutions that we can have for linear systems, and in particular, we'll talk about uh, a method for transforming a system of equations to a particular form um, that allows us to easily determine the solutions. And the method is called Gaussian elimination. Okay. Um, what we want to do is actually try to reduce our linear system of equations to a particular form that's called row echelon form, um, which I'll often abbreviate REF. And there's another related form that's slightly simpler that's called reduced row echelon form. And I'll usually take the additional steps to transform the system into reduced row echelon form, or RREF. So an echelon is actually a military term that refers to a particular arrangement of the troops where they're in like a stair-step formation. But let's look at the definition from the textbook. A matrix is said to be in row echelon form, and the will be called a row echelon matrix if it satisfies the following three conditions. All zero rows are at the bottom. The first non-zero entry from the left in any non-zero row is a 1, and it's called the leading one for that row, and then each leading one is to the right of all leading ones in the rows above it. It's in reduced row echelon form if it also satisfies the condition that each leading one is the only non-zero entry in the column. Okay, so this would be an example of a matrix that's in row echelon form. The leading element, which means the first element in each row, is a 1. All zero rows that are entirely zero are at the bottom, and then we may have the asterisk here represents just non-zero entries, or um, um, uh, so we may have entries above the leading ones, but the entries below the leading ones have to always be zeros. So this is echelon form. Row echelon form. Reduced row echelon form, we take the additional steps so that the entries above the leading ones are also zeros. So this element would be 0, these two elements would be 0, and then these three elements would be 0. And again, by using the matrix elementary operations, we can force that to happen. You know, if I subtract from row 3, let's say this last element here is a 4. If I subtract from row 3 4 times the fourth row, that will eliminate that element. And then likewise, I can use this fourth row to eliminate the elements in the last column above that leading one. So here's some other examples of row echelon form. And the asterisk just represent any numbers, but we've got in each row a leading one and then just zeros below that. And then the row echelon form, you'll notice above and below the leading ones, we have zeros. Okay. Now the row echelon form and the reduced row echelon form actually make it quite easy to determine the different types of solutions for our systems. The textbook gives a particular algorithm. It's called the Gaussian algorithm for reducing a matrix to row echelon form, and then an additional step for reducing it to reduced row echelon form. The algorithm is fine for computer implementation. You know, it generally has you divide the row by the first by the leading element to force that to 1. That results in a lot of fractions or decimal numbers. So I generally prefer to just use the elementary operations, and then avoid fractions until the very last step when I'm working through this by hand. So again, this is a fine method. It's a step-by-step recipe for producing, for transforming our augmented matrix to row echelon form. But again, I tend not to follow it exactly. So the goal here is actually to produce a matrix in row echelon form or reduced row echelon form. So let's actually look at this example. I want to talk about this in a little bit more detail. So we've got three equations and the three unknowns, x, y, and z. And the corresponding augmented matrix is this form. So in the process, the first thing we want to do, of course, we want to get a 1 in that first position in the first row. And so an easy way to do that is just swap 1 and 2. And then now we can eliminate the 3 and 4 in rows 3 and row 4, the elements below the 1, by subtracting from row 2 3 times row 1, subtracting from row 3 4 times row 1. That results in this. And then now we've got a leading 1 in the first row, a leading 1 in the second position of the second row. We can eliminate the 1 in the third row that's below our leading 1 by subtracting from row 3, row 2. That results in this. Okay. Now, anytime that in this process you get a result like this, so let me transform back to the whiteboard so I can talk about this in a bit more detail. So in the process here, this was the last matrix that we had after going through those series of steps to reduce the matrix to row echelon form. 5 minus 16 minus 3. But don't forget, this augmented matrix corresponds to an equivalent system, linear system of equations. Now, in particular, anytime you have a case like this with all zeros in the coefficient matrix part, and then a non-zero term in the constant part of our augmented matrix, what that row would correspond to is 0x plus 0y plus 0z is equal to minus 3, or 0 is equal to minus 3. That's, of course, an inconsistency. So anytime you see this, that means the corresponding linear system of equations is inconsistent and has no solution. So we can actually stop at this point. So inconsistent and no solution. So there is no XYZ triplet that would satisfy particular values of X, Y, and Z that would satisfy the original set of equations. Okay, let's continue then and look at the next example. So this is example 1.2.3 on page 13 of the text. Here we've got 3 equations and 4 unknowns. Here's the corresponding augmented matrix. I'm going to jump down to, this is actually row echelon form, leading 1s in each row or all zeros. This is row echelon form. If we eliminate the 1 above the leading 1 and if we eliminate the minus 1 above the leading 1 in this form, we actually get reduced row echelon form, and it's easy to do in this case. Just add row 2 to row 1. We'll get rid of that. And so here's the corresponding reduced row echelon form. Now, this last line corresponds to 0 equal to 0. That's consistent. Okay. Let me again flip back to a whiteboard and copy down this last matrix here. So this is example 1.2.3, and we got this result, 1, 0, 0, minus 2, 0, 0, 0, 1, 0, 1, minus 2, and 0, and then 2, 1, 0. And this is reduced row echelon form. All 0 rows at the bottom, if any. There won't always be an all 0 row. And then in each row, the first non-zero element is a 1. And then above and below the leading ones, we have just a column of zeros, except for the 1 in that column. So in this case, the variables that correspond to the leading ones in each row are called the leading variables. So in this case, x1, and this would be x1, x2, x3 are what are known as the leading variables, corresponding to the leading one. Okay. And then the other remaining variables, in this case x2 and x4, x2 and x4 are, I usually call them free variables. I think the textbook calls them parameters also. Okay, are free variables. This set of equations is consistent. Again, we don't have an inconsistency here. We have the 0 equals 0. What we can do for the free variables is just arbitrarily assign them parameters. So I'm going to let x2 equal s and then x4 be t. This is following the convention in the textbook where he lets the first free parameter be s, t, u, v, w, and so on. Now going back to my set of equations, I see that the second row here corresponds to, well, actually, let me just back up to the first row, would be x1 minus 2x2 plus x4 is equal to 2. So substituting in my parameter values, I have x1 minus 2s plus t is equal to 2. And then from the second row, I'll get x3, the one corresponds to my leading variable, minus 2x4, which I've assigned that the parameter t is equal to 1. So now I can solve these to find x1 and x3 in terms of my free parameters. And then so my general solution to this set of equations then is solving for x1 here. I'll have 2 plus 2s minus t. x2 I've assigned the parameter or free value s. x3 is 1 plus 2t. And then x4 is t. So this is the general solution to that original linear system of equations in this example. I can let s and t have any particular value. Let them both be 0, let s be pi, and t be 100. The corresponding point would be a solution point for that particular problem. We see in this case there are infinitely many solutions corresponding to an infinite range of values for s and an infinite range of values actually for t. So this is called the general solution in this case. Again, if we have the case where we've got zeros in the coefficient part and a non-zero term in the constant column, that's an inconsistency. This augmented matrix is consistent, and because we have free variables, there are infinitely many solutions. Okay, so let's look at some specific cases. I'm going to look at a couple different systems with 3 unknowns. Okay, so first let's look at 3 unknowns with 4 equations. Okay, so I'm going to look at the different possibilities in a little more detail than he does in the textbook. Okay, so with 4 equations, I'm going to end up with an augmented matrix that has 4 rows. Now here I've gone through, I'm just giving you the final reduced row echelon form. So after we've done our elementary operations, okay, and again, let's say we get something like this. I'm just going to write down arbitrary values here. Okay. But if we start with our 4 equations and then in reducing the system to row echelon form, I get a row like this at any time, with zeros in the coefficient part of the augmented matrix and a non-zero term in the constant part. I've got an inconsistency. I've got, in this case, 0 is equal to 4. So that's inconsistent. And that means I have no solution. The system of equations has no solution. Okay, just modifying this slightly. Let's say, though, I got this result. Again, having 3 unknowns and 4 equations. So I'm going to have 4 rows in my corresponding augmented matrix. But now, for a different system of equations, 3 unknowns, 4 equations still, in the process of reducing it to row echelon form, I get this result. This is consistent. Okay, with one solution. And actually, I can see the solution here. Remember, this row would correspond to 0x plus 0y plus 1z is equal to 3. And the first row would correspond to x equal to 1. So the solution here is 1, 2, 3. So there's a single unique solution for this corresponding problem. Okay. Now, I might, for, again, another system of equations, get something like this. 0, 4. 0, 1, 2, 0, 0, 0, 0, 0, 0. And then let's just say, maybe I got 1, 2, and then 0, 0 here. Okay. This is still a consistent set of equations. I've got all zeros here in the last 2 rows. I do have, so out of the 3 unknowns, I've got 2 leading variables, x1 and x2, and then I have a free variable, which would be x3. So here I've got, it is consistent. I've got 1 free variable. And so there are infinitely many solutions. Okay, as a matter of fact, if I let that free variable x3 or rather z be equal to s, then x will be 1 minus 4s. Y from the second row will be 2 minus 2s. And then the free variable, I've assigned the parameter s. So this is the general solution for this corresponding system of equations. Now, it could be possible even to get something like this, where I might have 1, 2, 3, and 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Still consistent. I've got 1 leading variable and then 2 free variables, so it is consistent. There are infinitely many solutions. The solutions would be if I let y have the parameter s and assign the parameter t to z, solve this first equation for x, it would be 1 minus 2s minus 3t, and then I've assigned the parameter s to y and t to z. So this is the general solution. It's in terms of 2 free parameters. Okay, so let's look at another case. So this would be the case again when we have more equations than unknowns. You know, I can have it could be inconsistent, could be consistent with one solution, or consistent with an infinite number of solutions. And this would apply for 5 equations, 6 equations, and 3 unknowns as well. Okay, let's look at the 3 unknowns and 3 equations case. Okay, so again, I might have something like this: 1, 0, 2, 30, 0, 1, 1, 20, 0, 0, 0, 10. This last row tells me the system is inconsistent. Okay. I might get something like this. Here, coefficient matrix has been reduced to the identity matrix, 30, 20, 10. Again, this would be for a different linear system. But in this case, I've got one solution. Okay. And it is unique. The solution would actually be 30, 20, 10 in this case, x equal to 30. And then, you know, I might have the case where, you know, I could have 1, 5, 8, and then the next 2 rows be consistent. So 30, 0, 0. Okay. Consistent, infinitely many solutions. I have 2 free variables. In this case, y and z would be free variables. I could have the case where there's only 1 free variable as well. So, you know, geometrically, the 3 unknowns here corresponds to the equation of a plane. So, with three equations, you know, if they're all parallel, then there is no solution. Or, you know, if the planes intersected along different lines, in that case there's no common point of intersection, that would lead to an inconsistent set of equations. For the 3 planes, you know, if they intersect in a single point, like 2 walls in the floor, that corresponds to this one solution case. I could have, you know, the 3 planes intersect in a line. In that case, I would end up with 1 free variable. Or if all 3 planes are actually coincident planes, overlapping planes, then I end up with the 2 free variables and infinitely many solutions. Okay, and then let's finally take a look at the case here where I got 3 unknowns and then 2 equations. Okay. You know, the possibilities are, you know, in general, might have something like 1, 2, 3, 4. Again, I'm just making up numbers here. 0, 0, 0, 8. And with 2 equations, that corresponds to 2 rows. The number of unknowns determines the number of columns in my coefficient matrix. Again, this is inconsistent. No solution. Okay, I might end up with something like this: 1, 0, 3, 0, 1, 2, 4, and 8. Notice this is in reduced row echelon form. Here, this is consistent with infinitely many solutions. And I have 1 free variable. You know, the third, I'd let z be the free variable, call it t. You know, the solutions would be of the form, you know, 4 minus 3t from the first row, and then 8 minus 2t from the second row. And then I've let z be my free, z is my free variable, and assigned it the parameter value t. And so the solutions would all be of this form. Okay, and then, you know, the other possibility might be something like this: 1, 2, 3, 4, 0, 0, 0, 0. It's still consistent. Here I have two free variables, infinite with two free variables. Again, with two planes, if they're parallel, there's no solution. They don't intersect. Two planes could intersect on a line. That would correspond to the one free variable case. Or if they're overlapping planes, coincident planes, then there's two free variables in that case. Again, in both these cases, an infinite number of solutions. There is no way for two planes corresponding to my two equations to intersect in a single point. They have to intersect on a line or be overlapping. So in this case, there is no single unique solution. We need at least as many equations as unknowns to get a unique solution. Okay. And then that brings me to the last concept in this portion of the lecture on rank. The rank of a matrix is the number of leading ones in the row echelon form of the augmented matrix, or the reduced row echelon form. They'll both always have the same number of leading ones. I'll mention also that the reduced row echelon form is always unique. There can be multiple row echelon forms. They all lead to the same solution set, but there can be multiple forms of the row echelon form, but the reduced row echelon form will always be unique. So in a consistent system of M equations with n unknowns, okay, and again I'm assuming it's a consistent set. If we let R be the rank of the augmented matrix, if R is equal to n, the rank of the matrix, the number of leading ones is equal to the number of unknowns, there is one solution. Okay. If R is less than n, there are infinitely many solutions with n minus r parameters or free variables. So I think that concludes the first two sections out of chapter 1. I'll assign some homework problems. I'll put up another video that's optional for where I'll work through another example of one of the problems at the end of the section, working through reducing a matrix, the augmented matrix, to reduce row echelon form and then finding the solution. So I'll put another example up. Also put up another example video on using octave to find the reduced row echelon form. And I'm going to ask that on your homework you go through this process. I know it's tedious. Go through this process of doing this by hand, but you can use octave to check your work. It is easy to make a lot of mathematical errors along the way. So again, use octave to check your work, but don't use octave to actually come up with the solution. Again, by going through this by hand, we learn a lot about the corresponding system of equations, and on the exam you may be forced to work through this by hand. So I think that's it for this lecture.